For doing these problems in section 4.7, we were asked to come up with a function in terms of a certain variable. There are some things from geometry and from algebra and algebra 2 that you want to keep in mind, just some situations and or formulas. So here we go. Looking at some special right triangles from geometry, our 30, 60, 90, and our 45, 45, 90 triangles. Our ratio of sides in the 30, 60, 90 is opposite the 30 if it's x, then opposite the 60 is x root 3, and opposite the 90 is 2x. It's kind of nice to just write it as 30, 60, 90, x root 3, 2x. And if I'm looking at that to get from opposite the 30 to opposite the 90, I would double. And to get from opposite the 30 to opposite the 60, I would multiply the side by 30 by root 3. And then thinking about how do I get from the 90 back to the 30 side if I'm given a 90 side. Well, if this is 2x and this is x, if I take the hypotenuse and divide by 2, that'll get me opposite the 30, and then go ahead and multiply by root 3, which would get you opposite the 60. If I'm given up it's opposite the 60, how would I get to opposite the 30? Well, I would divide x root 3 by root 3 to get x. 45, 45, 90, same kind of deal. My ratios are 45, 45, 90, x to x root 2, which comes directly from the Pythagorean theorem. You might want to confirm that. X squared plus x squared equals question mark squared. Solve for your question mark and you get x root 2. And same thing, if I want to get from the 40 opposite of 45 to the hypotenuse, I'd multiply by root 2. If I'm given the hypotenuse and I want to get a leg, x root 2 divided by root 2 equals x. So I would divide by root 2 to get back. So similar triangles. Let's suppose we have two triangles that are similar, and they're similar because of angle in this case. Both the little triangle here, the large triangle share this angle up here, and they both have congruent angles here. So by angle, those triangles are similar, and ratios of corresponding sides therefore are proportional. So B to B plus A, D to D plus C equals F to E. I might also remember from this setup that I had what was called the side splitter theorem, that if I take and in a large triangle cut the two of the three sides by a segment that's parallel to the third side, I set up B to A equals D to C. Note that B to A equals D to C is true, but that those two, B over A and D over C, are not equal to F over E. That F over E has got to come from making sure that you get side of similar triangle to side of similar triangle, side of similar triangle, side of similar triangle. Your side splitter, A and C, aren't sides. They're only parts of the large triangle sides. So another formula that's come up often in the past will continue to come up in this section. Distance equals rate times time, and our key idea here is if you got distance equals rate times time, you can get either the time or the rate in terms of the other two variables, and that might be useful for you setting up some of these problems. Another relationship that comes up for you to set up these problems, Pythagorean theorem. In a right triangle, square of leg plus square of leg equals square of hypotenuse. Now there are going to be a bunch of formulas that come up, geometric formulas for areas and volumes, and sometimes they'll give them to you in the problem. Sometimes you're going to have to look them up. Volume of a cylinder, pi r squared, that's the base area, times the height. The surface area of a cylinder, assuming it's got top and a bottom, well, that would be two circular bases, that's 2 pi r squared, plus the lateral surface area, that's the curved part. If you unfold a cylinder, you get a rectangle. The rectangle's dimensions are the circumference of the base circle, 2 pi r, and the other dimension will be the height of the cylinder, h. I might want to find the area of a trapezoid. That's the height of the trapezoid over 2 times the sum of the two bases. As remember, the bases are the parallel sides, and the height is the distance between those parallel sides. I might want the volume of a box, and generally if I have a base to a box, the base is going to have a length and a width, and then the height of the box would be h, the third dimension. And if I'm looking at a box, I might want to find the area of some box, and depending on if it has tops and bottoms, I'm going to want to make sure I add up the 4 lateral surface areas, the 4 sides of the box, and whatever bottom I might want to have. So if my box has a square base, for example, the area of my base with a width of W would be W squared. And then if my height of the box is, say, H, each side of the box is going to have an area of W times H, the dimension from the base square W times that height. So my surface area for a box with no top would be the base area, W squared, plus the four sides, 4WH. So some hints as you're doing these problems in 4-7. Number one, make sure you're tending to units. If you've got a problem and you're given meters and centimeters, you got to make sure whatever formula you're coming up with is either in terms of all meters or all centimeters. Second thing you want to make sure you're doing is once you've gotten your answer, make sure that your function gives you sensible outputs. You know, if you might want to try it out and make certain that the results that are coming out seem reasonable. And another bit of advice, if you want to get a function in terms of one variable, for example, cost is a function of length, or weight is a function of height, I might often have to create two equations and more than those two variables, and then use a substitution to get what I'm asked for.